Welcome to module number 7 of my YouTube-based circuit analysis course. The title of this lecture is Solving Basic Circuit Topologies. I think the name is pretty self-explanatory because we are going to discuss circuit types, let's say single loops, single node pairs, that are easier to solve, at least relatively, and compared to some of the circuits we're going to see later on in this course. Now, aside from that overarching idea, what smaller topics or subtopics are we going to address? We'll begin by talking about certain types of elements, and that's really a discussion of independent and dependent voltage and current sources. Then we'll dive into series and parallel connections for voltage sources, current sources, resistors, impedances, as well as the mathematical relationships that we use to define their equivalencies. And then we'll dive into those basic circuit topologies. So, how do you solve a single loop circuit? How do you solve a single node pair circuit? How do you use a voltage divider and current divider, both of which are derived from the former circuits we just talked about? And then also, slowly branching off, how do we solve a circuit that's almost like a single loop? How do we solve a circuit that's almost like a single node pair? Just close enough where we can try to apply some of those ideas that we learned previously. Like all my lectures, we'll employ plenty of examples to illustrate these ideas. And now why don't we begin by introducing the topic of independent voltage sources.
The first topic we'll discuss are various circuit elements, and we begin with the independent source. So the independent source defines a constant voltage or current between 2 points. So we have two different examples here. One is a constant current source as shown by the arrow in the center. One is a constant voltage source, which we can see by the plus and minus in the center. And I apologize, I think I'm using the term constant and independent here interchangeably. I'll try to focus more on saying independent. So an independent current source is one that defines the constant or fixed current between 2 points. Normally, we label the value to the side. So what we're being told here is that a constant known current, I beta, flows from point B to point A as exemplified by the direction of that arrow. Next, we take a look at the independent voltage source. So that defines a constant or fixed voltage between nodes A and B. And we've labeled it as V alpha. Now, generally, we don't need to provide two sets of the polarity labelings, and if anything, they should agree with one another, so we don't really need the second set. But we can use KVL, which we learned about last time, to tell us what V alpha really represents. If VA, or the voltage at node A, is positive, then that goes first. And if VB is the voltage at the negative node, that goes second, right? We're doing plus, positive minus the negative. So V alpha is equal to VA minus VB, which we could also call VAB. Now, if we were to flip those polarities, then we would have a different equation. V alpha would be equal to VB minus VA. And that would assume that we flip them in both locations. Now, one main difference between the independent sources and the dependent sources is the shape. So for a dependent current source, which we'll talk about what that means in a second, you'll still have the arrow in the center. And for the dependent voltage source, you'll still have the plus and minus in the center. But what tells us that these sources are independent, meaning they're not dependent on any other value, they're constant, they're fixed, is the fact that the symbol is a circle. Now, when we move on to dependent sources, what we'll see is that they use a diamond type shape. So that indicates that we're dealing with a dependent source. A dependent source defines, again, either voltage or current between 2 points. However, this value is not necessarily fixed, but dependent on another value within the circuit. So let's say one really easy way to demonstrate this is to think about modeling an amplifier, right? We know the output of an amplifier has a defined value that's dependent on what's being supplied to the input. So when we get to that point, talking about operational amplifiers, we'll see that the dependent source is a good tool for representing how that type of amplifier works. Now, there's 4 different types of of dependent source that we're going to talk about. And essentially that comes down to the idea of what the input is versus the output. All right, so we have voltage in or current in, and we have voltage out or current out. And so we have a voltage controlled voltage source. Okay, voltage in, voltage out. Then we have a voltage controlled current source because it's the voltage that controls it and the current that goes out. Then we have current controlled voltage source and current controlled current source. So those are what those terms refer to. Essentially, it's just the different permutations of either observing a voltage or a current and generating either a voltage or a current. So let's take a look at those down below. So here we have a voltage controlled current source. What we can see is that the shape is a diamond, as we would expect to see for any dependent source. We see that it has a plus and minus in the middle, telling us that it is ultimately a voltage source. If you look down here at our current controlled voltage source, it's still a diamond with a plus and minus in the middle, because both of these are ultimately dependent voltage sources. They may be dependent on different things, but they are both voltage sources. All right, so we have a diamond with a plus and minus in the middle. How do we know whether it's voltage controlled or current controlled? And what we're going to do is look at the equation to the right. Now, over here, we see that the voltage between nodes A and B is equal to 3/2 times V1 plus 2, where V1 is this voltage over here. Again, we apply the same use of KVL. VAB equals VA minus VB. We know that A is the positive and B is the negative because they're labeled. And that is equal to 3/2 V1 plus 2. So pretty straightforward. All you do is take the definition what's shown right here and you set it equal to whatever natural voltage that source would embody within the circuit. It's placed between nodes A and B. So we know that that represents VA minus VB. And all we have to do then is just stick in our formula right here. Now the current controlled voltage source, CCVS, still has diamond, again, still has plus minus, but you'll see this equation is dependent on a current, specifically the current I1 over here. And what we see is that VAB, still plus and minus, is equal to VA minus VB, that's nothing new, and that is going to be equal to 0.1 times I1 minus 0.03 volts. Now, I'm not going to go into units too much, but one would assume that this 0.1 has a units of volts per amp because we're multiplying it by I1, which is in amps. So generally, the units should work out in that way. But voltage controlled voltage source, current controlled voltage source, both of them dependent voltage sources, but the difference is just what they are dependent on. Then we have the current controlled current source and the voltage controlled current source. They're both diamonds and they both have arrows in the middle to indicate that they are current sources. They define a current. I hope that by this point it's becoming a little bit more evident what I'm going to say with regard to these. Okay, we know here that because this is current controlled, it's going to be some function of another current. Here I just put a generic F of I1. And what we see is that IAB is equal to some function of I1. If the arrow went in the other direction, we would have IBA as a function of I1, right? You have to be careful that we're paying attention to that direction. The voltage controlled current source, same thing. Now we have F of V1. All we do is replace F of I1 with F of V1, and there's no assumption that these formulas are the same. They're just generic F. So you should be familiar with these terms. You will see the abbreviations often used: VCVS, CCVS, CCCS, VCCS. So ultimately, I don't think you necessarily need to be able to throw the answer out immediately, but if you look at it for a second, hopefully you can decipher exactly, what type of dependent source that is. So we've talked about independent voltage and current sources, which have a fixed, assumed to be scalar, let's say scalar value. Okay, then we have dependent voltage and current sources, which generally will have some sort of a functional definition, that function being dependent on some other value in the circuit. So those cover the vast majority of the ideal sources. Okay, we haven't really used that term, but these are ideal sources because, they operate in an ideal manner. There's assumed either no internal resistance for the voltage source or infinite parallel internal resistance for the current source. We assume that it's completely linear, etc., etc. So, generally these are idealized representations of real sources. You do not find real sources that operate in this way over large operating ranges, for the most part. We've already talked about what a resistor is. Hopefully, we know that a resistor or any constant impedance defines the relationship between the voltage and current through that element as defined by Ohm's law. This is the symbol for the resistor, and this is Ohm's law. We know that R equals V over I. And here we are assuming that the passive sign convention is being applied. Now, the reason why we say a resistor or any constant impedance is because, for DC circuits, we don't have to worry about complex impedances. For DC circuits, constant static voltages and currents, the imaginary parts of the impedance go away. But for AC circuits, where we do have to consider the imaginary, we would use the complex form of Ohm's law, which is that Z, the impedance, is equal to V over I, again obeying the passive sign convention. Now, I'm not going to talk about this too much here because we have talked about resistors and we have introduced Ohm's law previously, so I don't think there's a need to rehash a lot of this. A ground, and I think we've talked about this as well already, but briefly I'll discuss it again. I apologize for the repetition. So a ground, sometimes referred to as earth, is a reference point that represents a grounding electrode conductor buried into the ground, and we can assume that this point remains at 0 voltage. It's essentially an infinite sink or supply of current. It can consume as much current as it needs to, and it can generate as much current as it needs to. Now, a ground is not going to, by nature, act like a current source. It's not going to provide the differential which allows that current to flow. But if there are other elements in the circuit that are drawing that current, it can supply the quote-unquote electrons. So why bury it in the ground? Essentially, the earth acts like a charge source or sink with near infinite capacity, and the ground protects the circuit against unusually large currents, such as those associated with faults. So if we take a look at this very simple system here, we have some kind of electrical circuit. We have a grounding wire, a grounding rod, and let's say for some reason there's a very huge jump in voltage and or current, coming into this HVAC unit or whatever that may be. You can essentially send that surge down into the ground where the current would dissipate through assumed to be infinitely large earth, and it wouldn't affect your machine as much. Now, for many problems, we will use a generic reference point that's assumed to have a 0 voltage. We don't really, for many theoretical problems or textbook problems, we normally don't really talk about whether it's grounded or not. We just use them as some sort of an ideal sink or ideal source. So if we call something a reference point and we say that it's known to have 0 voltage, it doesn't really matter for our purposes, again, for textbook purposes, whether it's grounded or referenced in some other way. Okay, so I've decided to include these homework problems in the lectures as sort of glorified examples. I do recommend that you go through them yourself without looking at the answer first. I think they're a good practice. But let's jump in here to a problem. So we want to define the voltage between points A and B, VAB. Okay, so taking a look at this circuit right here, this is one place where I would say don't make an easy problem into a difficult one, because, let's say someone's first inkling may be to say, okay, well, I know that VAB is equal to whatever this resistance is here times IAB. And I could calculate IAB using some version of KCL and then, go through all that work. And that is a valid way to solve it. But there's an easier way. We see here that this voltage source is in parallel with these 2 points. The voltage here is AB. So we already know that VAB is equal to 10 times I3 plus 1. So we don't really care, and that's the reason why that resistance value is not even listed, because you don't need that for this problem. All right, so we don't know I3, unfortunately, right off the bat. This value is not given. However, we can apply KCL at either node C or, node C makes the most sense, at node C. Okay, so if we take a look at node C right here, and I know we haven't had too many examples of having to apply KCL, so let's do it slowly. At node C, we have essentially 3 branches connected, right? We have one that's conducting I1, we have one that's conducting I3, and one that's conducting I2. And you can see that I've used the same directions as in the circuit, right? I2 is heading into node C, I1 is heading into node C, and I3 is heading out. So if we apply KCL, we end up with this right here. I3 equals I1 plus I2. Or the current flowing out of the node is equal to the sum of the currents flowing into the node. All right, we're told that I1 is 3 amps. We're told that I2 is negative 1 amp. And so that leaves us with 2 amps. Don't get thrown off by this negative right here, okay? If you remember something I said in one of the previous lectures, the direction of a current and its sign for textbook purposes, right, are independent from one another. We can say a current is flowing from D to C with an amplitude of negative 1 amp. Just like it would be somewhat logical to say, I am driving from Detroit to New York at a speed of negative 50 miles an hour, which I guess would imply you're actually traveling from New York to Detroit, the opposite direction. Okay, and so we plug in our 2 amps here, the same, using that same equation up above, and we end up with a voltage of 30 volts. So, two takeaways here. First, how do we analyze a circuit with a dependent source? And then also, again, just being careful to not make problems more difficult than they need to be, potentially. Next, I want to discuss series and parallel circuits. So we've introduced the different elements, or some of the different elements that we're going to work with in this course. Independent sources, dependent sources, resistors, impedances to some point. So what about the different ways in which they can be connected? Because that's really the missing piece between the knowledge you have now and the knowledge needed to solve some of these more complex circuits. A series connection is one that is characterized by 2 branches or elements who share only one common node with no other branches connected to that common node. So here I have 2 examples, one that is in series and one that is not in series. R1 and R2 are in series. Why? Like I said above, they share one common node and there's nothing else connected to that common node in series. Down here, we see that R1, R2, and R3 are not in series. Or we could say none of them are in series. R1 and R2 are also similarly not in series. Although they do share a common node, the fact that there's something else connected to it as I wrote here, messes it up. Now, it is possible to have 3 resistors in series, but that's essentially just by association. So if we have R1, R2, and R3, we could say that R1 is in series with R2, R2 is in series with R3, and then therefore the 3 of those would represent a series connection. This is something that students often mess up in the beginning, thinking that just because 2 elements share a common node, that they're in series. So series connections of resistors and voltage sources have equivalence. Current sources don't. We'll talk about that in a second. Meaning that they may be represented as a single element. So what I'd like to do is kind of split this up into 2. The top half deals with resistors, bottom half with voltage sources. Let me do that a little bit better. All right. So what we see here are 2 resistors, R1 and R2, and they are in series. There's nothing else connected here. And therefore what we can do is we can take their endpoints A and B, which we move over here, A and B. Don't change those endpoints. The equivalent resistance between those is equal to R1 plus R2. You'll note that node C is gone, right? It's no longer observable in this simplified representation of the circuit. So to make a more complex topic, to say it in a more basic way, resistors add or sum in series. Now voltage sources do something similar. We see here that voltage source V1 and V2, they are in series with one another. They share a common node with no other connections. We're going to take the 2 endpoints, which are VA and VB. Okay, we move them over here. And now the equivalent voltage between those 2 points is V1 plus V2. Now, this is according to KVL. So we have to be careful here that our polarities are the same, right? If we're assuming that our polarity is A is positive and B is negative, that means that the voltages add if they have that same polarity. Positive, negative, positive, negative. If for some reason this were flipped, V2, this would become minus V2. So it may be helpful when you're first getting used to doing this, making series equivalencies for voltage sources, that you use KVL and pay special attention in doing so. I've written a little mini equation over here. Right? We see that VAB can be broken down into VAC plus VCB, right? This is independent of the actual sources themselves. We're just using the subscript notation. Then we can break VAC into VA minus VC. We can break up VCB into VC minus VB. These cancel out. And what you're left with is VA minus VB or VAB. All that really shows is that this equivalency is consistent, okay, as long as we're taking into account the polarities of these sources. So real quickly, why can't we connect current sources in series? I don't want to spend too much time on this because it's not in the notes, but really quickly, let's just show. So let's say I have a current source here. There's a midpoint. I have another current source here. And I'm going to say, I'll call this IA equals 2 amps, and then IB equals 3 amps. So what is the equivalent current flowing through this branch? You can see here that unless these 2 values agree, we have an inconsistent, physically unrealizable solution, right? Because we can apply KCL. We know the current flowing in should be equal to the current flowing out. In that case, that would be 2 amps flowing in, 3 amps flowing out, and that obviously doesn't work. So generally, we don't connect current sources in series unless, there's some sort of issue where we need to generate more power, but we're not going to talk about that. So for the purposes of this course, we don't discuss current sources in series for the reasons that I just stated. All right. So now talking about parallel connections. So a parallel connection is characterized by 2 or more branches or elements who share both common nodes. Parallel connections for resistors and current sources have equivalence. So let's look at this example here. R1 and R2. They are in parallel because they share both of these elements, and there's not a rule that nothing else can be connected there. So if there's something else connected over here, that does not change the fact that R1 and R2 are in parallel. Okay? Now, I drew it here in sort of a more freehand form. This is generally the way that I would draw it in a circuit diagram. And so what we can see is that the equivalent resistance between these two nodes, which I'll again call A and B, is equal to this equation. Now, I didn't label the nodes here, but that's really important to do. When drawing equivalencies, we need to make sure we understand between what two nodes, or between what, in some cases, multiple nodes, that equivalency applies. And so R equivalent is equal to R1 times R2 over R1 plus R2. The easiest example of this is two equal resistors in parallel. So let's say this is 2 ohms, this is 2 ohms. What you end up with is 2 times 2 over 2 plus 2, which is 4 over 4, which equals 1. Quick rule of thumb, right? Whenever you put two resistors in parallel that have the same value, you end up with an equivalent resistance that's half that. So if R1 were 150 and R2 were 150, you would end up with an equivalent resistance of 75. There is another form of this equation right here. You can say 1 over Req is equal to 1 over R1 plus 1 over R2. And what that's really saying is that the admittances or conductances sum when in parallel, because this is really our equivalent conductance, right? Those sum. So the resistances sum in series and the conductances sum in parallel. Excuse me going back and forth between admittance and conductance, but again, for a DC circuit, it doesn't really matter. And we're going to revisit these rules when we get to AC circuits and be more careful about discussing them in terms of impedances specifically. All right. Now, voltage sources, we don't discuss the parallel connection of voltage sources, pretty much for the same reason that we don't discuss the series connection of current sources. Because if we connect two voltage sources in parallel, they should, by default, have the same value in order to be physically realizable, right? If they don't have the same value, then we're essentially going to have conflicting values. The voltage between A and B will say, 5 volts is equal to 4 volts, which that doesn't work. All right, now let's talk about currents in parallel. So currents in parallel, they sum. And, right, this is more of a freehand way of drawing it. This is how I would draw it in a circuit diagram. And what we see here is that the currents I1 and I2, because they're in parallel, they sum. But again, just like how we talked about applying the equivalency to the voltage sources, you have to make sure you're taking into account the direction. Okay? If our I equivalent is assumed to be flowing upward, then that means that it will be composed of the sum of those two currents, assuming they also have the same direction. If I2 were flipped around, then you would have I1 minus I2. And all of this comes from simply just applying KCL at that node right there. KCL tells us that I equivalent, which is the current flowing out of the node, will be equal to the sum of the currents flowing into it, which in this case is I1 plus I2, unless we flip that direction of the current source, and in that case it becomes I1 minus I2. So, what I would say is that these equations here, okay, they more tell you what to expect what form to expect for series connections of voltages and parallel connections of currents. But generally, because of the sign problem, I recommend you rely on KVL and KCL to actually come up with the value. Fortunately, we don't have that problem with the resistors because they're non-directional values, and so R equivalent equals R1 plus R2. Regardless, I mean, there's really no directional component to it, which makes it easier. And so we can generalize the expressions above with these two equations. So I actually already showed this right here. Okay, I said that it was 1 over the equivalent resistance is equal to 1, the sum of 1 over the resistances that compose it. And that's essentially what this equation here is saying, except it's expanding it to the n number of terms. So because there's no requirement for the parallel connection that nothing else be connected here, right? We can connect other things if we wish. We can actually we can generate an equation that applies to a larger number of resistances. And same thing over here for the currents. This, as you imagine, looks a lot like KCL. Okay. Now, Delta-To-Wye conversions or transformations. The parallel and series equivalencies, right, allow us to simplify or expand a circuit based on, right, we know these certain equivalencies exist. We learned 4 of them, right? There's series and parallel equivalencies for resistances, which will later on expand to impedances. We have the series connection equivalency of voltage sources and the parallel equivalency for current sources. But there are some cases where resistances can be connected such that the parallel and the series cannot be used, those equivalencies. And a prime example are the Y and the delta configurations. So they get their names from what they look like. As you can see here, we have 3 nodes, A, B, and C. And they are connected by a Y-type connection of 3 resistances. If we wanted to simplify this subcircuit, okay, between the 3 nodes, or among those 3 nodes, we can't use parallel or series connections. RA, RB, and RC are not in parallel, nor are they in series with one another. And if we go over here and look at our delta, we see, again, those same 3 points, A, B, and C, and 3 resistances, RAB, RBC, and RCA. And none of those are in series or parallel with one another, assuming that there's other stuff connected here. Now, if we assume that nothing else is connected at node B, then yes, I mean, these two are in series with one another. But we wouldn't use this equivalency unless there was an assumption that there's other things connected at these nodes, preventing them from being in series with one another. So a lot of talk. What does this mean? The Delta-To-Wye transformation allows us to go back and forth between these 2 forms. We can take a circuit in the Y-connected configuration and find out the equivalent values which make it delta. It's important, however, to note that these 3 points, A, B, and C, they must remain the same. You can imagine that we are cutting this part of the circuit out, removing it like a piece of paper, then taking this and putting it in its place. But it's very important that the A line up with the A, the B line up with the B, and the C line up with the C. The same way, when we did other kinds of equivalencies, it's important that we understand A, B, B. For any of these equivalencies, it's just as important to know the value as it is to understand exactly where it's supposed to go. Okay, so why is this useful? Well, because there are going to be certain types of problems where this transformation, either going in one direction or the other, allows us to perform other simplifications, which then allows us to solve the circuit. So we'll go through an example which will show that. We're going to focus mostly on the balance case, and the balance case is when RA equals RB equals RC, which in turn means that RAB, BC, and CA all equal. So these three equal to each other, but they don't equal these three. These three are equal, these three are equal, the two groups are not equal to one another. So how do we perform that conversion? Now, when the system is balanced, we don't need to talk about RAB, RBC. We can just call them all R delta, right? All three of these we'll just call R delta. Same thing over here, we'll call all three of these RY. Okay, so how do we perform the conversion if the resistances are balanced? What we see is that we know RA, RB, RC, they all can be given the name RY. This is for the Y connection. For the delta connection, RAB, RBC, RCA, they can all be given the name R delta. And this equation here, RY equals 1/3 R delta, allows us to go back and forth. Pretty straightforward. Essentially, the Y-connected resistances have 1/3 the value, the resistance of the delta-connected versions. Now, we also have equations for the unbalanced case. I'm not going to talk about this too much. So if RA, RB, and RC are not equal to one another, you can use these three equations in order to determine the corresponding delta terms. So this would be an example of a Y to delta conversion or transformation. I'm not going to read out all the terms. I think you could see that on your own. Over here we have the Delta-To-Wye conversion, where now it's in terms of RAB, RBC, RCA, although you can see it's repeated. And essentially you put the unbalanced terms in and you would get three different values. You can use this for the balance case if you wish. It's a longer way, as compared to this equation above, but it will still generate the same value. The Y to delta is something that, my background is actually in power systems, and in power systems we use the delta-Y and Y to delta conversion pretty heavily. It plays a role in this course, but it's not one that we're going to see all the time. One reason for that is because once we move on to nodal and mesh analysis, our need to perform these types of simplifications is lessened slightly. All right, so now let's get into what I consider to be the meat of this lecture, because last lecture we talked about different components and basic laws and stuff like that, but there wasn't really a lot of practical application. And in the beginning of this lecture, we talked about, again, more types of components, specifically different types of sources, different types of connections, but we still haven't gotten down to the meat of solving problems. At least not really complex problems. Now we're going to start that with a look at the single loop circuit, because the way that this course introduces topics is we'll look at the simplest examples and then we'll slowly build up to more complex ones. So a single loop circuit is one that is relatively easy to solve, okay, given the tools that we have recently acquired. A single loop circuit is one with a single current flowing within it, right? Whenever you have a single loop, that means that all of the elements are going to be in series with one another. V1 is in series with R2, R2 is in series with Fx, Fx is in series with Z3. And so we can apply KCL at each one of these nodes, and we'll see that whatever current is flowing through one of the branches is flowing through them all, and we call that I loop. So there is only one current I loop that flows through all these components. It will serve as the state for this system. Okay, I'm not sure if many of you are familiar with that term state. We will talk about it in slightly more formal terms later, but the state is generally a value or set of values which provide the most fundamental description of the system's behavior. So once we solve for that value, that I loop current, we can easily solve for pretty much everything else, right? We can get the voltage here, V2, by simply using Ohm's law. Now, the nice thing about the single loop circuit is that we can use one KVL expression to describe the entire circuit. And we can use that one KVL expression in order to solve. I feel like the best way to exemplify that is going to be jumping into an example. So the example starts here. It asks us to solve for the loop current IL below, as well as the voltage V2 for this single loop circuit. Now, I'm not always going to tell students when the circuit is a single loop. So this is definitely something that you should be looking for in the beginning when you are presented a circuit, especially this early on in the course, is be checking, is this a single loop circuit? Because that could make this a lot easier. All right, so let's take a look at what we have. We have a independent voltage source. Again, it's a circle or an oval, so we know that it's independent. And it has the plus and minus on the interior, so we know it's voltage. Then we have a resistor and a second resistor. This is actually a very specific type of circuit called a voltage divider. All right, since this is a single loop circuit, we know that we have a current, which we call IL, flowing all through there. And what we did was, first thing, we're going to label all the circuit elements, all the circuit voltages, all the circuit currents. And I think I've suggested this several times before, that you start off your problems in this way. We don't need to label any more currents because, right, we have that same IL flowing through all of them. So it's assumed, right, we don't need to label those again. We did already label V2 as having a positive and negative terminal as shown. We haven't labeled V1, so I'm going to go ahead and label it as such. Now, why did I label it plus minus in that way? Because I wanted to obey the passive sign convention, which if we have IL flowing in that direction, right, then we would be obeying the passive sign convention, which is what I want, at least in the short term. Other than that, pretty much everything is labeled. We know what the polarity of Vs is, it's plus minus, and so we can go from there. Now, it's a single loop circuit, so we know that we can write out KVL for this entire loop and essentially solve it in one step. But we need to be careful about the signs of these voltages. So let's use the trick that I used previously. What I'm going to do is I'm going to imagine that we have this loop that follows the direction of IL going all the way around. And I'm going to use that to determine the signs of my voltages. Okay, what's positive, what's negative in my KVL. All right, so starting from here, let's go around and write out KVL. So I'm going to assume that V1 is positive because IL goes between its positive and negative terminals. So any other voltage in this loop where IL flows from its positive to its negative, that will down here be reflected as a positive voltage. Let's go take a look at the other values. What about V2? For V2, we see that the current does flow from the positive to the negative terminal, so that also is positive. What about Vs? Over here, we see that Vs is the opposite, right? IL, if we imagine it as being this red loop, is flowing from the negative to the positive terminal, which gives us minus Vs, and we're back at the start, so that equals 0. So this is how I would write out KVL. If we take a look at the version down here, we can see that's exactly the same thing, except with all the signs flipped. I guess that when I wrote it out originally, I had assumed that Vs was our positive reference. Regardless, I think being able to properly define KVL is a really, really important part of this class, and you really can't progress on to harder problems if you're making, or you can't succeed in the more difficult problems if you're still making mistakes with KVL. So stop here. If you don't understand why this is plus Vs minus V1 minus V2, you should definitely pause here and take a look and make sure that you can help yourself to understand. All right. Now, step 3. So we went through, step 1, we labeled everything. Step 2, we wrote out KVL for this loop. Now, we want to solve. Unfortunately, this equation, as it's written here, there are more unknowns than we have expressions, right? Vs is known, but V1 is unknown and V2 is unknown. So what we want to do is we want to put this in terms of a single unknown that we can solve for. Or at the worst case scenario, we want to have an equal number of expressions and unknowns. Now, one way that is often used is substituting for Ohm's law. So what we can do is we can use Ohm's law to define V1 and V2 and then sub them into the equation above. Remember that up here, when we looked at the direction of IL, we defined the polarity of V2 and V1 both such that they obeyed passive sign convention. Again, if we consider V1 and IL or V2 and IL, that means that V equals IR or V equals ILR1, V2 equals ILR2. We don't have to worry about any negatives. And that again is the beauty of trying to rely on the passive sign convention as much as possible. So anyway, we substitute those two in here. And what we end up with is an equation with only a single unknown, which is our IL. Our IL. And we can solve for IL using this form right here. Or actually, this is an intermediate form with the solvable form being this right here. We know that Vs is equal to, 5 volts. What was the R1? Oh, they're both 1,000. So this ends up giving us 5 over 1,000 plus 1,000, as shown right here. And we solve and we end up with 2.5 milliamps or 0.0025 amps. So that's one of the values that we were looking for, which is IL. Again, the direction is that which is specified by that purple arrow right there. We started out the problem assuming that IL flowed in the clockwise direction. And so the answer, the numerical answer, relies on that assumption. So the current is 2.5 milliamps flowing clockwise. The problem also asks us to solve for the individual voltages, and that's pretty easy using Ohm's law, which we had already specified here and here. We know R1, we know R2, and now we know what the IL values are. We go ahead and stick those in. I don't know why I just didn't put the numerical value, I guess. Well, I know why I did this. We'll get to this in a second. But anyway, when we plug in the IL value, we have 2.5 milliamps times 1,000 ohms, and we end up with 2.5 volts. Now, why do I have this work down here? Because we can also solve this circuit symbolically, okay, without knowing what the numerical values are. For that, what we're going to do is we are going to write out KVL for this entire circuit. So let's take a look here for 1 second, because I want to provide a little bit of background as to what this equation is referring to. We have a single loop. All of these elements are in parallel with one another, right? In series. All of these elements are in series with one another, which means that we can combine resistors together. I'm going to give these names. I'm going to call this A, B, C. So node A, node B, node C, and that's a short, so node C. Then I'm going to redraw something over here. This is node A, this is node C. And we can have a single resistor between nodes A and C, which is R1 plus R2. So we can call that R equivalent. This circuit is pretty easy to solve. And again, I'm showing sort of an alternate way to solve this problem, which is fine. IL still applies. We know that IL, we can just go ahead and apply Ohm's law directly. IL is equal to Vs over the R equivalent, which is R1 plus R2. So what we end up with is Vs over R1 plus R2 for IL. Now if we take this symbolic value and we plug it in to this equation right here, we replace IL with Vs over R1 plus R2, and the R2 stays where it is. So hopefully you understand the relationship between this equation right here and this equation right here. All that we did was replace IL with this definition, symbolic definition of IL. And when we do that, what we end up with is this equation here. And this is the basis for the voltage divider. What it tells us is that if we have a circuit that takes this very specific form, two resistors, and actually this applies to impedances as well, I'm going to give them slightly different names. I'm going to say R1, I'm going to call it the series element. Okay, and R2, I'm going to call it the load element, because we assume that we're observing this second resistance. Then the voltage across that second element always takes this form. It's going to be equal to the original source times the ratio of the second resistor over the first plus the second. And so that is, in addition to the single loop circuit, a specific type of single loop circuit that you can be on the lookout for. So let's talk about the voltage divider specifically. We've already introduced it, so we know what a voltage divider is. The example above, we just finished it, demonstrates how a special type of single loop circuit behaves, and we call that the voltage divider. This circuit allows us to step down voltages when need be. Let's say your remote needs only 1 volt, but your battery provides 1.5 volts. Now this is not actually a very good example. The reason being, this setup would waste tons of energy from your battery. The voltage divider steps down the voltage by essentially dissipating tons of energy as heat, which has the side effect of reducing the voltage. But it can be useful for certain applications, especially if the current is very low. So what we have is this circuit here. Now, one thing to make note of is, well, first off, we already know that this circuit corresponds to this equation. We can calculate the voltage across R2 by multiplying the initial source or the input source by this ratio. But this is very specific to the exact arrangement of these elements. Not necessarily the order of them, but across what element you're observing the voltage. Because let's say, for example, we want to observe the voltage here across R1. If I were to call this V1, I'll say plus minus, that would be equal to Vs times R1 over R1 plus R2. The reason for that is because we always put the resistance across which we're observing in the numerator. The denominator would stay the same. Now the other thing here is that the polarity of V1, should mirror the polarity of Vs. As you can see here, the polarity here is plus minus. That means that the corresponding polarity over here needs to be plus minus as well. As we get further into this material, I'm not going to pull out KVL or KCL each time to justify how these polarities are defined. When you see something like this and you question, well, why does V2 have to have this polarity and Vs have to have this polarity in order to have a consistent or an accurate solution, I recommend you go back to an example like this up above and play around with some of the orientations of this stuff. Let's say we want to observe a V alpha, and that has the opposite polarity. And take a look at how the derivation affects the final result. Otherwise, we can often get bogged down by trying to add tons of assumptions and clarifications for every single equation, where I don't even necessarily know if that would be the best way to learn it. There is a certain amount of experimentation that is involved here. You do need to do the homework problems, do practice problems, and become more familiar, let's say inherently, as to why certain rules and certain correlations exist. Okay. So that's the voltage divider. It's very useful. You will see it a lot of times, especially in these introductory circuits courses. So hopefully you'll be familiar with it. You'll be able to note when you see one and apply the appropriate equation. Okay, so now, almost a single loop. So what do we do here? This goes back to my question as to how to teach this course over multiple years, because we would often start off with single loop and single node pair. We haven't talked about single node pairs yet, but single loops and single node pairs. And then there's kind of this jump to just doing more complex circuits. And, we tried to extrapolate the lessons that we learned from a single loop or a single node pair and apply them, but I don't know if that part was really clear. So I added this section, which almost a single loop. And what that means is, we can find circuits that resemble a single loop pretty closely and apply similar rules to them. So, what if we have a circuit that is almost a single loop? Can we still solve it? Yes. What's the formal definition of almost a single loop? There is no formal definition. Okay, I'm going to talk about why the circuit below, for that circuit, why I feel that it's almost or resembles a single loop. But in the end, right, this is more of let's say a soft definition. So, if we have a circuit that we feel is almost a single loop, how can we solve it? We can use equivalencies to reduce our circuit to a single loop and then solve it as a single loop, which we already know how to do. However, now during this process, we will lose access to certain values eliminated by this circuit simplification process. We've seen that before. Let's say we have two resistors in series. Okay, I'll call this node A, B, and C. And we simplify that to a single resistor across nodes A and B. Okay, R equivalent. We no longer have access to that node C. Okay, we can't inherently determine what the voltage AC is from this circuit over here. So that's what I mean when I say we will lose access to certain values. A more formal way is we will lose the ability to observe certain values. But that's okay, because the simplification can be undone. Right? We can, in the same way that we can use the parallel and series connection rules in order to simplify the circuit, we can also use those in combination with what we know to expand it back out and regain access to some of those variables. Okay, so let's take a look at this circuit right here. Now, why is this almost a single loop? The reason why I would say it's almost a single loop is because you have a resistor network here that I'm pretty sure just by looking at it, we can collapse into a single resistance. We know, I can just observe that these two are in series, and then that would be in parallel with this. So just from looking at this, I kind of know that I can make all this into a single resistance. And if I do, then we have a single loop. So again, I don't know if necessarily everybody is going to like or appreciate the way that I'm presenting this here, but there's a certain level of intuition. I think it's a little bit more of an intuitive way to describe how to jump from single loop circuits to more complex circuits than simply just saying, okay, here's a circuit, do what you can do. So the way that I visualize this is almost like collapsing an accordion. So we're taking this piece here and we're pushing it in order to get rid of all of that and end up with a new equivalent resistance. At the end, if we want to regain, let's say we really need VCD for some reason, we can use those same rules to push it back out. Now, then you might be asking, well, why bother collapsing it if I can just expand it back out? I mean, how is that easier? Because when it's in its collapsed form, it will be really easy to calculate this current right here. Then when we expand it back out, we may not know the current here and the current here, but we know that the sum of those two is this IS. And so, when we expand it back out, there's still information that we can use from the collapsed form or the simplified form that's relevant. So, is there any way to collapse the highlighted portion of the circuit above? Yes, there is. Okay, and I kind of already showed it. If I redraw this section of the circuit like this, perhaps it'll seem a little bit more evident to some of you. Okay, where this is node B, this is node C, this is node D, and this, sorry, no, I wrote that incorrectly. This would be node B, this would be node C, and this would be node D. Okay, and so this is R2, R3, and R4. And what we see here is it's pretty evident that these two are in series, and the series equivalent of those two together is in parallel with R2. And so hence that leads us to the equation over here. The total equivalent resistance for that whole network, which will be between nodes B and D, okay, is given here. First thing we do is we connect the two R3 and R4 into as a series connection, which we could give it another name if we want to. We could call it R34. And then that whole thing is in parallel with R2. I don't think we use this symbol specifically. Those two parallel lines are simply just a shortcut for indicating in parallel. So if we wanted to write this out using the mathematical form we learned before, we know that that will be R2 times R equivalent. And when I say R equivalent, I'm talking about those two together. Actually, I don't want to use R equivalent again. Let me call this R 34, because it's the combination of 3 and 4. Okay, R2 plus R34. Okay, and then now what we can do is replace the R34 with R3 plus R4. I don't know if I'm going to have space here. And we end up with the equation for this equivalent resistance, including all of those together. R2 times R3 plus R4 over R2 plus, if we wanted to, we could put parentheses here, the sum of R3 plus R4. Okay. So once we do that, we collapse this part of it in, we can redraw our circuit as shown here. Vs takes the same value. R1 takes the same value. Any voltage, let's say we had already determined VAB, that would take on the same value. The VBD we have represented right here, that's the same VBD we would see up above if we were to span the voltage between those 2 points. However, in this circuit right here, right, we no longer have access to point C, and we can no longer observe resistances 2, 3, and 4. However, we've achieved one of our sub-objectives, which is to make it a single loop circuit. We know how to solve this pretty easily. Okay, and so not only is it a single loop circuit, it's also a voltage divider. So that makes things easier. So we see here that VBD, which is, we're assuming the voltage we're observing, is equal to our initial source voltage times the resistance across which we're observing plus the sum of both of those resistances. So in this equation, where we used R2 above, we're calling R equivalent here. We can't use R2 again because R2 has a different meaning for this circuit. All right. Now, what we know is that VBD is equal to all of this. Now, finding the numerical value is irrelevant. I think we didn't give numerical values here, right? So we don't really care about the numerical values, but we know that we have a solution to finding VBD. What if we wanted to find the voltage across R4, which, if we go all the way up above, would be VCD. We know VBD, but we don't know VCD. And in the simplified version of the circuit, VCD doesn't even exist, right? We can't see it here. So let's go back to our expanded version of the circuit, which I apologize got split between 2 pages here. All right. But hopefully you can see it's very similar in form to what we have up above. I know what VBD is, and so I can calculate VCD in a similar way. We see that VCD across R4 can be easily solved for using the voltage divider again, right? Because if we look, we can imagine VBD, since it's a known voltage, we can imagine it being its own voltage source between nodes B and D. And so that gives us, and I'll redraw down here because I know this page split was not a great spot for that. Okay, we have R3, we have R4, we have VBD, and then we have whatever else is going on over here. It doesn't really matter what's going on over here. The nice thing about a voltage divider is that there's no rule that nothing else can be connected on the other side. Okay, anything else can be connected over here. It doesn't matter. As long as we know the voltage between 2 terminals and we know that it's connected to 2 series resistors, the voltage division, that equation will apply. All right. So we know that VCD, which is the voltage across R4, will be equal to the source going into it, which in this case is VBD, times R4 over R3 plus R4. We're just taking that voltage divider and using it down there. Then what we can do is take our value of VBD that we got above from right here and plug him in below. And so what we would end up with is our initial VS over, what is it? R equivalent over R1 plus R equivalent. That gives us VBD. Multiply that by R4 over R3 plus R4. And that will give us VCD. So what you see is we used a simplified version of the circuit to determine VBD. And then we use an expanded form of the circuit in order to determine VCD. Now, how do you extrapolate this process to even bigger circuits? I think for that, you really have to lean heavily on the homework and the example problems. If you're not taking this course with me in person, then that will probably mean looking at some additional problems online. And that, I would say, for the most part, you don't need instruction there. In fact, less instruction is good for those homework problems. You need to be forced to figure them out yourself. So, I mean, that's the general process, though, that I would say is this accordion-like sort of movement, okay, where what we're doing is we're taking larger circuits, okay, which may have, may go off in multiple directions, and we're pushing it down, collapsing it down to a single loop. Now, does this work for every type of circuit? I mean, most definitely not, right? If you have, for example, a nonlinear element over here, or you have dependent current sources, then, that's not going to work. In fact, I would say for this early stage of the course, you probably don't want to try this simplification if you have dependent sources. Or if you have multiple source types. So for example, let's say over here there was a current source. It might make this more difficult, although you could use a Thevenin to Norton conversion or Norton to Thevenin conversion, but we haven't gotten to that yet. So, I mean, it's baby steps here. And what I mean by that is, and perhaps it's better to say incremental steps. We're incrementally learning how to solve more and more complex problems. And that is okay. That is the way I would recommend to learn this, is to slowly increase your abilities, as opposed to looking for, I know that some courses focus on these, larger, overarching, more general methods and equations that, they are correct, but I don't know if they're necessarily the best to help someone learn. All right, so let's take a look at another one of these homeworks that I've kind of downgraded to an example problem. We want to solve for the voltage across R4, which is VCD. As you can see, this is very, very similar to, to the problem above. Really, the only difference being that we have a current source here instead of a voltage source. So we're not going to be able to rely on the the voltage divider, but that's okay. So first thing we'll do is we'll label all the nodes. And what that also, what it does is it alleviates the need to label all the voltages, because we know VAB looks like that. We know that VBD looks like that by the very nature of the subscripts. And because there aren't any parallel single segments, we don't really need to label all of the currents. I guess it is a little bit ambiguous because both this and this could be referred to as IBD, but I'm going to say that, we're only using the subscripts to refer to a single segment. So this is IBD, this is IBC, and this is ICD. You can label it however you want. Okay, so we have a circuit that is quote unquote almost like a single loop. It's not completely a single loop. And, what we see is we can probably collapse this down into a single, resistor. So we're going to use the same equations that we had above. We want to find an equivalent resistance between nodes B and D, which replaces this whole thing. And it'll leave us with an equivalent circuit that looks like this. We have node A, we have node B, we have node D. This is R1, and this is what we're going to call our equivalent. It helps sometimes to imagine what your circuit is going to look like after the simplification, and do that before you actually simplify. That way you kind of know what to expect. So this R equivalent, again, same situation. We have R2 in parallel with the series connection of those two together. So we use the same math. I gave this series connection a name Rx, and we plug in the values. So we have, let's see, 1,000. This is 500. This is 250. And so anyway, we end up with a value of 428.5 ohms. And then we have a simplified version of the circuit that looks like this right here. Okay, now, I apologize again for it cutting off part of the page. I can't get it all on the same page without it causing other problems. But, so what do we know? This is not a voltage divider. Okay, so, well, how can we solve it? Well, let's go back to the fundamental question, that we pose ourselves for a single loop circuit. To solve a single loop circuit, we need to know what the current is through it. And then from that, we can calculate pretty much anything else. The current through all the branches is the same. And we know by definition that the current through a current source is defined. So this current going all the way around is all equal to IS, or 1 milliamp. And then what we can do is we can solve for VBD using Ohm's law. IL times R equivalent. We're obeying the passive sign convention. And so that gives us 428.5 millivolts. That makes sense because we had 428.5 ohms and our current is 1 milliamp. Now, what we did is we drew the revised circuit as shown here. Now, I'm going to be honest with you. I traditionally don't replace things with sources. It was a visual trick that I think that helped students in class at the beginning, but later on, it perhaps proved to be a little bit detrimental. So if I were to write this now, I would probably just leave this as a resistor, but say that the voltage across it is known. Anyway, so now we can pretty much repeat the same steps as we did for the example. We know VBD. If we just look at this portion of the circuit right here, we can imagine it as a voltage divider again, where we're trying to observe the voltage across R4. So that gives us VBD, which is our quote-unquote source being applied. It's a known voltage. And we have 250 over 250 plus 500. And that leaves us with, okay, it's all shown right here, 428.5 times 1/3, which gives us 142.7 millivolts. So, again, a good example of what to do when you have a circuit that's almost like a single loop, but perhaps not quite. Now, earlier on I talked about single loops and single node pairs, and I said those were the simplest circuits to solve. So there is one other type of what I would consider fundamental circuit topology that's easy to solve, single node pair. So a single loop is easier to solve because there's only one current flowing through it, right? It gives us a bottleneck, a point at which, if we can determine that state, everything else can be determined from that state. With the single node pair, we have a similar situation, except it's the voltage, not the current, that acts as the system state. So a single node pair, the easiest way to identify it is it only has one pair of electrically independent nodes, right? There are only two electrically independent nodes here, A and B. All right. The voltage across all of these elements is exactly the same, which we'll call Vx, or I could call it VAB. And so, right, they're all in parallel, just like in a single loop circuit, everything is in series. In a single node pair, everything is in parallel. In a single loop circuit, they all have the same current flowing through them. In a single node pair, they all have the same voltage across them. So, we know there's only one voltage. We know that, or I'm going to tell you that we're going to consider it to be the state of the system. Once we solve for Vx, we can essentially find any other value, and we can use one KCL expression for the entire circuit. For the single loop, we relied on KVL because we're trying to get, we relied on KVL, and for the single node pair, we rely on KCL. That'll become apparent in a second. So for this, unlike the single loop, I'm not going to spend as much time going through and deriving everything. I think the easiest way is going to be to sort of just jump into an example, and I think naturally we'll start to see where things can be solved for. But again, the whole goal is to get that Vx value. Once you have that, you can get anything else. All right. So this example asks us to solve for VP. Where is VP? VP. Okay, I'm assuming that's labeled later. Solve for I3 as well as I4 in the circuit below. Actually, I know what VP is. VP is the assumed voltage across the entire circuit. So it's what I called Vx up above. All right. So, right, we can see first, let's check to make sure if this is a single node pair. It is, right? Because we have node 1 and then that stretches all the way over here. We have node 2 and that stretches all the way over here. There's no shorts between them, so we don't have to worry about that. All right, so we're good. So we do have a single node pair. We know that we want to get this value first. We want to get our VP, what I called VX, up above first. So how can we do that? Well, we can combine current sources together and resistances together in order to simplify the circuit, although we don't really have to. I could just go ahead and solve this using KCL at node number 1 or node number 2. Okay, because what I can say is that this I equivalent right here is going to be equal to IS1 minus IS2, which is 0.5 milliamps. And then that I equivalent is going to flow across the parallel combo of the two of those together. So I could say VP is equal to I equivalent times the parallel connection of R3 and R4, and then I'm done. But we could also simplify further first, and that's the way I did it in the problem. So we'll go ahead and present it in that way. All right. So what we're going to do is combine both the current sources into one, as well as both the resistances into one. So I already showed how to do this. I equivalent, since it's leaving this little subnode right here, it's going to be equal to the sum of IS, which is flowing in the same direction, minus IS2 because it's flowing in the opposite direction. Then we can come up with an equivalent resistance for both of these together, which is R3 times R4 over R3 plus R4. So we have an equivalent circuit that looks like this right here. We have an 0.5 milliamp source flowing upward or to the right, again, as exemplified by IEQ. And that's flowing across a resistance which has an equivalent value of 166.6 ohms. So this is a single node pair. We can go ahead and solve for our IEQ. Actually, we already know IEQ. All right, so we can solve for our V pair. That'll be equal to IEQ times REQ, and that's what is shown down here. So that gives us 83.3 millivolts. And so now let's take a look at what we know. So we know I equivalent and we know what I'm calling V pair. How does that map to this circuit up above? Okay, we know this voltage and we know the current flowing along the short at this point. The only value that we're missing I3 and we're missing I4 of what we were asked. You can see there's a pretty easy way to solve for that. We know I3 would be equal to VP over R3 and I4 would be equal to VP divided by R4. So we could do it that way. That's relatively straightforward. And that's what's shown right here. But this type of circuit is a variation on another subset of the single node pair that we call the current divider. So the voltage divider is a special type of single loop circuit, and the current divider is a special type of single node pair circuit. And it looks like this. So again, one special type of single node pair is the current divider. This circuit allows us to divide or step down currents. So in the same way that the voltage divider allowed us to step down voltages. Now, one thing I should say here is that, we cannot step up from the source. Same thing goes for voltage or current divider. We cannot generate a voltage higher than the source coming into it, nor can we generate a current that's higher than that's applied to it, because we don't have any additional sources for energy. So what we see is if we have a current source that is flowing through two parallel resistances, similar to how the voltage divider had two series resistances, then these easy, pretty basic equations tell us automatically what the values of I1 and I2 would be. So if we're observing across this resistor, we use this equation. If we're observing across this, we use this. Now you may look at these and say, oh, these are the exact same equations. They're a little bit different. They obviously have the same form, but the main difference is that when we're observing I1, it's not R1 that's in the numerator. It's the opposite resistor. And then vice versa. When we're observing I2, it's R1 that ends up in the numerator here. So, I mean, in my mind, I kind of think of voltage divider and current divider having like an opposite sort of mathematical expression. Although, I mean, that's really, that's up for interpretation what you mean by opposite. But it always reminds me that, one has its associated resistor in the numerator, and then the other one, the current divider, has the quote-unquote other in there. Okay. Now, you can expand both the current divider and the voltage divider to work for more than two elements. So, for example, you can build a current divider with, multiple values over here, and you can adapt the math for that. Same thing for the voltage divider. I'm not going to go into that too much right now because I think that's encroaching on, the lesson relating to single loop or single node pair circuits. So I'll let you take a look at that yourself. Okay, now let's take a look at one of these sort of, homework problems that are no longer really homeworks. And we're asked to solve for I2 from a single node pair. One thing to watch out for is, a homework problem or a quiz or exam problem. I guess it depends on who teaches it. They won't always tell you that it is a single node pair or a single loop. So you should be actively scanning and looking for those. So we know that this is a single node pair. There's only two nodes, node 1, node 2. There is a voltage that I'm going to call VP across all of them that's shared. And so we're off to the races, right? We want to solve this. Now, one thing that I probably haven't talked about enough is the combining of voltage, current sources, resistances, and what order has to do with them. For both KCL and KVL, the order of the elements is irrelevant. Okay, so if I have this circuit right here, and I decide to move the current source here and move the resistor over here, it really doesn't have an effect on the operation, the behavior of the circuit. Same thing if we had a single node pair, a single loop, and we had something like this. This is still a single loop, right? We could push these two together and then move the resistances together and make something that looked like this. And that would still be equivalent. It may, screw up the ordering of the nodes, but as long as you're consistent, you can do that. So, it's not necessary to move these elements around here. I think it does help in sort of visualizing what's going on. So I'm going to move the elements around. Okay, first thing I'm going to do is I'm going to collect the two current sources together, and then I'm going to collect the two non-observed resistors together. Because if you remember, up above here, it tells us we're only solving for I2. So we only need to know the current through R2, so we can lose the visibility or the observability for R4 and R5. Okay. So when I make this rearrangement, or I rearrange these elements, what we see is that these two will sum in parallel, and these two can be combined in parallel, which then will yield us a simpler circuit, right? We'll have a current source, we'll have our R2, and then we'll have another R equivalent over here. This looks like a current divider, right? We saw it up above here. even though I drew on it so much we can't recognize it anymore. But it looks like a current divider. Okay, so let's go ahead, before we jump too much ahead, let's complete the simplification. So what's the I equivalent? The I equivalent is going to be IS1 minus IS3. Why not plus? If we look up above here, we can see that we have determined the direction of I equivalent as flowing upward and to the right, depending on how you want to look at the orientation. The flow of IS1 matches it, IS3 opposes it. And that's the reason why I equivalent is equal to IS1 minus IS3. Again, it's really important. Signs of currents and voltages in this class can really mess you up. Okay. So we know that I equivalent is 9 milliamps. And then R equivalent, we'll go ahead and calculate that using R4 and R5. And what we end up with is a current divider that looks like this. In this picture, I actually switched the locations of R2 and R equivalent, but again, it doesn't really matter here. This is our equivalent value determined from up above. This is the value that was known, and this comes from up here. And then we can go ahead and apply our current divider equation. This is 9 milliamps. This is 70 something. This is 1,000. And what we end up with is 600 microamps, or 600 times 10 to the negative 6 amps, flowing along the branch for I2. Now, let's see if that makes sense. Right, we know that, we know that the current will flow along the path of least resistance. So if we look at here, forget about that. I'm gonna represent that as the 9 milliamps. Okay, so imagine that this is both of those put together. So IS1 and 2. Okay. So we have 9 milliamps flowing like this. And they have a choice. I mean, that's not really the word to use, but right, the current has to be divided between the 1000, the 250, and the 100 ohm resistances. We would expect for the most current to flow here, less to flow here, and the least to flow here because it has the highest resistance. So it makes sense in some way, shape, or form that the I2 value we calculate is small. It's less than 1 milliamp, it's about, that's 0.6 milliamps, right? So 600 microamps. And that makes sense more or less with what we see in the circuit above. Doing checks like that, I mean, perhaps, they may not be easy for everyone in the beginning, but as you become more familiar with the circuits, I think doing physical checks, looking to see if things make sense, can be helpful. One thing that would definitely stand out is, let's say we got an I2 value where the current through it was 100 milliamps, right? We're already going to be asking, there'll be a lot of red flags there because that value is higher than the current we even have coming into the circuit. So as you get better and better, or more experience with these types of problems, hopefully, you can get a better sense, better intuition as to what types of answers you expect for certain types of problems. Okay, almost a single node pair. Pretty much the same thing as what we talked about for almost a single loop. I don't really spend that much time explaining it, but it's a pretty similar process. We look for circuits that resemble single node pairs and that we feel like we can use relatively low effort simplifications in order to make it into a single node pair. So if we look at this deprecated homework here, we want to solve for V3. And we're being told that this is almost a single node pair, and that kind of makes sense because, right, I could see that if I just combine these together, that would eliminate this node and we would have a single node pair. All right. So first thing we're going to do is label all the nodes, all the currents, all the voltages. Again, I apologize for this being split on 2 pages. So, right, this is not really here because it's shown up above. Same thing, this is shown up above, and this is shown up above. I know it's not the best presentation, but hopefully you can see, right? We have a current source, we have this resistor, and this resistor, and nothing. Essentially, there's nothing here on the bottom. 3 nodes, of which we're going to eliminate this one by combining R2 and R3. Okay. So, right, I don't think we even drew the simplified circuit because it was so easy, right? We know what it's going to look like. It's going to look like IS, R2, and then, so this is IS, this is R2, and we already know this is R2 plus R3. So we can just jump straight to using the current divider. We know that this current, sorry, this is 1, not 2. Okay, so if we want to figure out this current right here, IR1, which I'm assuming, no, that's not what they're asking us for. Okay. Well, there's multiple ways to approach this. I think the way that I'm doing it here is I want to determine the voltage VR3 and then go back and calculate the current. Okay, so what we do is we solve for IR3 using the current divider as shown here. We know that IR3, which hopefully is labeled up above, okay, that would be this current right here, is equal to IS times R1 over R1 plus R2 plus R3, when in reality that's the equivalent. That gives us 300 microamps flowing along this branch right here. And then we know the current flowing through R3. It's pretty easy to calculate VR3 using Ohm's law.